Hello students, in this video we'll discuss the relationship between the Riemann Zeta function, the gamma function, and a power of pi, which will give us a function called the xc function, which helps us to symmetrize the Riemann Zeta function. So let's recall some basic facts. Recall that we have the Riemann Zeta function, which we just defined, and this is going to be the sum. N goes from 1 to infinity of 1 over n to the z. And we've defined this for all real values of z greater than 0, right? Which is great. And so now what I want to do is I want to connect this with the gamma function, which we've previously done, but with a slight twist, and define a function theta of t, which is the sum n and z, e to the negative pi n squared t, okay? We've seen that this is a version, in some sense, it's a version of the heat kernel. So we know by Poisson summation formula that this is going to be equal to 1 over the square root of t, theta of 1 over t, and that follows from Poisson summation. Poisson summation. Okay, excellent, because I know the Fourier transform of the Gaussians itself, right? So I rescale a Gaussian, I get exactly this formula, right? Remember that Poisson summation says that if I have a reasonably defined function, the sum of n and z of f of z is equal to the sum n and z of f hat of n, like that. That's the Poisson summation. So I use that in this theta function. Now I'm going to define a new function, define psi of t is going to be what? It's going to be 1/2 of what? So of course, if n is positive or negative, doesn't matter, right? Those are the same values. So if I do half of theta of t minus 1, then that function is going to do what? It's going to subtract off the 0 term, and then it's going to split the even and odd terms, right? So this will be what? The sum from 1 to infinity of e to the negative pi n squared t, right? And this series, of course, converges for all values of t greater than 0. Great. Excellent. So this is defined for all t greater than 0. Okay, that's great. And so now what I want to do is the following. Now I'm going to connect zeta and gamma in our traditional way, right? So now let's consider the integral from 0 to infinity of u to the what? To the s over 2 for a complex number s minus 1, and then psi of s ds, okay? What's this going to give us? Well, this is going to give us this infinite series over here, right? So this is going to be what? This is going to be, I'm going to pull interchange the summation and integration, right? This is going to be the sum, n goes from 1 to infinity, of the integral from 0 to infinity of u to the s minus 2 minus 1. And then we're going to have this thing over here, e to the negative pi n squared, and then I have a u over here, or then I have an s, right? This would be an s, and I want this to be a what? I want this to actually be a u. So I'm sorry, that should be a u. We want this to be u integrals. So u and then u. Okay. There we go. du. And so now what we're going to do is the following. So now we want to change this into something that looks like just a pure exponential over here. So what I want to do is I'm going to replace this over here. So I'm going to look at the new variable over here. We're going to define t is going to be n squared u, like that. Great. So then what's dt going to be? So dt is going to be n squared du, okay? And then what does our integral become? Our integral becomes the sum, n goes from 1 to infinity. The integral, of course, limits don't change under this coordinate change, 0 to infinity. And we're going to have a u, which is going to be a t over n squared to the s over 2 minus 1. Great. And then what? And then we're going to have a times what? Times e to the negative. And I want to put a pi over here as well. So let's put a pi over here as well, times pi, and then times pi, like that. Great. And then I'm going to have to put a pi over here as well in the denominator. So that's going to be a n squared over pi. So I have a u, and u is going to be t over n squared with a pi, like that. Excellent. And now this n squared pi n squared u is going to turn into a what? That's just going to turn into a negative dt, right? That's going to be negative dt. And then we have a dt, which is n squared times pi times du. Okay, that was a lot of change of coordinates. So let's make sure we have everything all tidied up. So this is going to be the sum, n goes from 0 to infinity. Let's count the numbers of n's we have. So I have an n squared to the s over 2. That becomes an n to the s, an n to the negative 2, and an n to the positive 2. So those will cancel out, right? And I'll have a 1 over n to the s. That's great. That's what we want. Then we have the integral from 0 to infinity of what? I'm going to have a pi to the what? Pi to the s over 2. Like that. But that's going to be the denominator, so it's a negative, right? And then we're going to have a what? Then we're going to have an e to the t, and then a t to the s over 2 minus 1, e to the negative t dt, like that. And so what is this, of course? This is, of course, just going to be what? That's going to be zeta of s. Zeta of s. That's going to be pi to the negative s over 2, and that's going to be gamma of s over 2. Beautiful. So this integral gives us, this integral over here exactly gives us what? Exactly gives us this product of these three functions. And so I'm going to define that function to be xi of s. And so what is xi of s? It's zeta of s, pi to the negative s over 2, times gamma of s over 2. Okay, excellent. Okay, so this is the xi function. This plays an important role in the study of the Riemann Zeta function, okay? It symmetrizes the zeta function for us. Now, of course, I have this relationship over here, so let's find out what the Poisson summation formula tells us about psi, right? So let's look at root u psi of u. That's going to be root u times what? Times just theta of u minus 1 over 2, right? And now what do I know? If I know that theta, I know that from this formula over here, I know that root t times theta of t is equal to theta of 1 over t, like that. And so what we're going to do with this expression over here is we're going to sort of, well, I'm going to multiply this through, so this is going to be a root u theta of u over 2 minus root u over 2. And now, of course, what I would like to have is I'd like to have a what? I'd like to have a, now, I know that root u theta u is going to be this theta of 1 over t, so this is going to be, this is going to be equal to theta of 1 over u, theta of 1 over u over 2, and then minus root u over 2. Good. And so now, of course, I'd like to see a what? I know that theta of 1 over t minus 1 over 2 is going to be psi of 1 over t, like that. Great. And so I need to see a psi of 1 over t, so I'm going to add and subtract in a 1 on the top here. So this is going to be equal to theta of 1 over u, and I'm going to say minus 1 over 2, and then I have to add in a 1/2 minus root u over 2, right? And therefore we have our final relationship that I can conclude from this. So note, we're going to make this following note now. Note is that psi of u is really the same as what? Is really the same as, this is going to be a psi of 1 over u, 1 over root u, psi of 1 over u, and then a what? And then a plus root u over 2. Good. Those cancel out actually, so that's going to be in the denominator. Let's be careful here. So I want to what? I want to plus 1 over 2 root u, and then a minus 1/2, okay? Beautiful. And now this formula is going to help us out a tremendous amount, because what I can do now is I can plug that into the formula over here and conclude what? I can conclude that xc of s, for example, is going to be this integral over here, right? Is going to be this integral, is the integral from 0 to infinity of u to the s over 2 minus 1. And then instead of psi of u, I'm going to plug in this thing over here, 1 over root u psi of 1 over u, and then plus 1 over 2 square root of u, right? Good. And then a minus what? And then a minus 1/2 du. And we're going to split this integral into two parts over here, right? The first part of the integral we're going to split is we're going to split this into the integral from 0 to 1 of this expression. plus 1 over 2 root u minus 1/2 du, and then plus the same integral over here from 1 to infinity. Call this thing over here just g of u, and I'll put a g of u du over here. Good. Now here's the kicker. I can explicitly integrate this thing over here, right? Because I'm going to have an extra factor of 1/2, right? So this is really s minus 1 over 2. So that's just going to turn into a what? When I integrate this thing over here, I'm going to get a 1 over s minus 1. And I'm going to get a 1 over s over here, right? For these 1/2. So this integral over here is going to integrate to 1 over s minus 1. This integral over here is going to integrate to minus 1 over s. And then I will change the coordinates. I'll let zeta be 1 over u, and then that will turn that into the same thing over here, right? So then plus the integral from 1 to infinity of just a u to the negative s over 2 minus 1/2 plus u to the s over 2, and then what? And then minus 1, and then finally just a psi of u du. Great. And so what this allows me to say now is the following. This formula over here it doesn't matter if I replace s with 1 minus s, right? So this formula allows me to conclude that xc of s is xc of 1 minus s, right? Excellent. So now we have our fundamental relationship for the Riemann zeta function, which says that what? It says that zeta of s, pi to the negative s over 2, gamma of s over 2, is equal to what? Is equal to zeta of 1 minus s, and then pi to the negative s minus 1 over 2, right? And then gamma of 1 minus s over 2. Now from that relationship, that allows me to conclude the following. It allows me to conclude that these zeros of the zeta function, that zeta's going to have some zeros, right? It's going to have some zeros where this thing over here has poles, right? And that, of course, has poles at -2, -4, -6. So the poles of this function over here, -2, -4, -6, have to correspond to the zeros of this thing, because there's no zeros over here, because we're showing it's well defined over there on the strip when s is bigger than 1 in modulus, right? So we've been able to use this formula, this xc formula, to conclude the very special property that there is this symmetry of the Riemann zeta function about the line s equals 1/2, right? About the real part of s equals 1/2, and that's the critical line for the Riemann zeta function. And that gives you a sense of why the critical line is so important, because this xc function over here, which is a relationship between zeta, pi, and the gamma function, tells you there's implicit symmetry of the Riemann zeta function about the line real part of z is equal to 1/2, the critical line, and that's where the Riemann hypothesis pops up. It pops up from exactly from this symmetry, and that gives you a clue as to where you think most of the zeros will occur. They should occur on that critical line, and that's the reasoning behind the Riemann hypothesis. Thank you very much.